Okay, so last time we saw like a couple of applications. Okay, let's start from a new page of BFS and DFS, and today we'll see some algorithms on, or basically one particular algorithm and some notions of BFS and DFS on directed graphs. So let's look at, so what is it, 21st. Okay, so let's look at directed graphs. Okay. So so again, I'm not going to redefine the notion of directed graphs and all. So as I had said, you are supposed to revisit yourself and then see what are the notions. But just like so edges are directed, that we know. So UV, if it is an edge, it has a direction and it will be written as UV as a tuple. Okay. And now in the representation, if we have the adjacency list, right? So what will the adjacency list look like? So every node V or every vertex V will have two lists instead of one. Okay. And what are the lists? Incoming neighbors and outgoing neighbors. And we denote this by n minus V, and outgoing neighbors n plus V. So suppose this is V, all the vertices that which have edges 2V, these are n minus V, and all the vertices that V has an edge 2, they are n plus V. Okay. So this is the notion of incoming neighbors and outgoing neighbors. Okay. Good. So what about BFS and DFS on directed graphs? So I mean, this you must have seen, like the incoming neighbors and outgoing neighbors and so on. All right. So what now BFS will do? So suppose we start the BFS from in a directed graph from one node, and then we go to this. Then we look at all the out neighbors of S. The first layer L1 is out neighbors of S, or let me just say n plus of S. Then second layer is going to be n plus of L1 set minus whatever has been discovered earlier, and so on, right? So we can do exactly the same thing, and we'll just be accessing the outgoing neighbors list. But so this is just the notion of BFS. But what does this BFS compute? Anyone? So what will be the output of the this BFS? The nodes that are coming, which are in L1, L2, and so on. What are those nodes?
The nodes reachable from S.
Yes. So it computes the set of nodes reachable from S. And as we know in directed graphs, you might have a path from S to T, but that might not necessarily mean that you will have a path from T to S. So this might mean that these nodes might not have a path to S, or so this is informal, like S might not be reachable from these nodes. Okay. So what is the concept? So the concept is of, as we say, mutually reachable. Yeah, and if we want, suppose, if we want all the nodes from where S is reachable, then what can we do? Suppose we wanted to now, in first we started from S and found out all the set of reachable nodes from S. Now we want to find out all the sets from where you can reach S. What
So
can we
instead
do?
of looking at the outgoing edges, we'll look at the incoming edges and perform BFS.
So we can reverse all the edges and then start a BFS from S.
Yes. So the first one, how do you like? Yeah, it's not really incoming edges, and then
So you said no, every node has two lists now. A list of all the
yes,
outgoing edges and a list of all the incoming edges. So I thought we could
yes.
perform all the incoming edges that from where S is reachable, layer 1, then layer 2, and so on.
Okay. Yeah, 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 even that might work actually. Yeah, exactly. So that might work, but that is exactly what you instead of doing for incoming edges, another way is just reverse the edges and then you do the normal BFS for outgoing edges. You will get to the same edges.
Yes, sir.
Yeah, right. So whatever incoming is incoming will become outgoing, and then you will get the same. Okay. So reverse the arcs and do BFS. Again, so you can do BFS, and it is not hard to see that DFS also produces the same set. Okay, good. So this you can convince yourself that why DFS will not be anything different. Now there is this notion of strong connectivity. So before that, if there is a path from U to V and from V to U, then U and V are called, let's say, mutually reachable. Right? Let's denote it by okay. So a graph or a directed graph, of course, G is strongly connected if for all U and V in vertex set, we have U and V are mutually connected. So there is a path from U to V and there is a path from V to U. Okay.
So the path need not be same, right?
It will not be the. I mean, it will not be the same by definition because the outgoing edges are different from incoming edges.
So
So
that's
to
what I'm saying. That it is not necessary, right? That if there's an edge from U to V, there need to be an edge from V to U.
yes, 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 definitely not. So this is just some some directed graph. So that is a special kind of directed graph, which is called bidirected graph, in which if there is an edge from U to V, then there is an edge from V to U. But this is just some directed graph, and in this, and even then, even in a bidirected graph, the paths are not the same. I mean, they might traverse the same vertices, but the paths in case of directed graphs, then you have to look at the edges, and since they are traversing different edges, they are not the same paths actually. Okay, good. So now, how to test whether a graph is strongly connected? So, any ideas for this?
we can take an arbitrary node and see if all the nodes are visible. Like we can reach all the nodes from there, and then we
Yeah.
can reverse the edges and see if we can reach this node from every node as well.
Okay, yes, that's correct. So pick an arbitrary S, do BFS, sorry, reverse the arcs, again do BFS from S, and if both of them reach all the vertices in graph, the graph is strongly connected. So let's just quickly just look at the proof sketch. So look at any two vertices U and V. Suppose S is somewhere here, or if any of them is S, then of course from the previous thing we know that if U is S, then V can be reached from S, because we do a BFS and then V comes in that BFS, and then the set of all vertices reachable from where S is reachable. So if this U is equal to S, then there is a path from V to S also. So that is fine. So these cases where U or V is equal to S is okay. Now suppose not. Suppose not, then there is a path from S to U. There is a path from U to S. There is a path from S to V. There is a path from V to S. And using these, you can see that there is a path from U to V, and there is a path from V to U. This is path from U to V, and this is the path from V to U. Okay. So this is just just to show that the graph is strongly connected. So that we can check in order n plus n time, because all we are doing is BFS, right? Okay, good. So also, what is so this is a notion of connectivity in directed graphs. So just like we had with the notion of connectivity in undirected graphs, we had this notion of connected components. Similarly, with this notion of connectivity, which is strong connectivity in directed graphs, we have this notion of strongly connected components, okay, in directed graphs, right? So strongly connected component. So we say strong component or strongly connected component. Okay. So S subset of V is a strongly, or is a strong component if for all UV belonging to S, we have U. Okay. And then we can show a lemma. It's not very hard. That is, all the strong components in a graph are either disjoint or identical. Okay. And why you can show this? Any ideas?
This is the equivalence relation.
Yeah, you can show this to be an equivalence relation if you include identity sort of thing. I mean, yeah. So proof you can try yourself. So if you add identity, then it becomes an equivalence relation, and because of that, they are either disjoint or identical. So now, just like finding all connected components, the question will become that can we find all connected components? Okay. So find all strong components of a directed graph. And that is also very similar. But slightly more work is needed, and this is like exercise. Try this on your own.
So could you please explain that lemma once more?
Lemma just says that all the strong connected components in a graph are either disjoint or identical. So let's say S and S1 and S2 are two sets which are strong connected components. So you mean the statement of the lemma? Okay, let me first explain the statement of the lemma and then we'll see. Okay, so what is the lemma saying? That all the strong connected components in a graph are either disjoint or identical. So let S1 and S2 be two strong connected components of the graph. So strong connected components is defined as a subset of the vertices, right? So now what does this say? That either S1 is equal to S2 or S1 intersection S2 is equal to empty set. Okay. So what you can do that if S1 intersection S2
Yeah, got it, Sachin.
okay, is not equal to empty set, then there exists something in the intersection, and then from there you can reach all the vertices, and then you can say, I mean, so if you want, you can show this to be an equivalence relation, but there is a more direct proof also. I mean, yeah, whatever you find easier, it's okay. Okay. So yeah. So good. So now we have so this is just to talk about the analogous notions of connectivity and so directed graphs are slightly more complex, as you saw that if there is a path from S to T, it does not necessarily mean that there will be a path from T to S, right? And so they are slightly more complex objects. In fact, they turn out to be more complex in most of the applications that we'll try to do. So if we try to generalize something on undirected graphs to directed graphs, it turns out to be significantly harder. Okay. For example, if we look at this acyclic graphs, right? So what are acyclic undirected graphs? What is this? The undirected graphs which don't contain a cycle, what are they?
Forest.
Forests. Or in other words, every connected component is a tree. But what about directed acyclic graphs? So they are also called DAGs. Okay. And here we don't want any directed cycle. So one good thing about the forests is that they are very sparse, can have at most n-1 edges, right? The maximum number of edges a forest can have is when it is a tree and then it has n-1 edges, right? But now let's look at this concept of directed acyclic graphs, graphs which do not have any directed cycle, right? So how many edges they can have? Is it necessary that they have only n-1 edges or some linear number of edges?
No, sir.
No. Yeah, so that's correct. So I mean, you can just make let me make one graph which is not exactly a tree, and then I'll just orient the edges Yeah, so suppose you do this and then whatever, you do this, then you do this, let's say you, yeah, then you do this. So this graph you can verify later that it does not have a directed cycle. So does not have a directed cycle, but it has greater than n-1 edges, right? In fact, so these can be much more complex than trees. And can have many more edges, of course. In fact, they can have all the pairs for all edges for all the pairs. How? Can anyone guess? So a graph which has edges for all the pairs but does not have any cycle.
Sir, we can put them in a straight line, a horizontal line, all the vertices, and make the edges and direct them all to the right side.
Exactly. So you have 1 to n, the set of vertices, let's say, and then ij is an edge for every I less than j, right? So here between every pair of vertices there is an edge. So how many edges does this graph have? It has n choose 2 edges, and still no directed cycle. Why? Because as Manish you said just now.
Yes, sir.
Yeah. So as Manish just pointed out, because you can put all the vertices from like 1 to n in this order, and all the edges are going forward. So to get a cycle, you have to come back, right? So this is a concept we'll revisit again. So you can like convince yourself that there is no cycle in this graph as all the edges are going in the forward direction. Okay, good. But we'll come back to this in like slightly more detail in another context actually. Okay, good. So now there is, why do we worry about this sort of thing, like like directed acyclic graphs or DAGs, right? So there are some applications, and one typical application is in like operating systems and things like that. So one application is dependencies, and you want to resolve dependencies. We don't want circular dependencies. What do we mean by that? So suppose job A depends on job B, which in turn depends on job C, and so on, something like that. So you have job A that depends on job B, so you can put a directed edge. Then that depends on job C, you can put a directed edge. Suppose B depends on some, or some D depends on the B, then A also depends on E, something like that. Okay, and then you have something like this, whatever, so you can have this this very complex dependency graph, but you don't want a cycle there, or if there is a cycle there, that is a bad thing. So you want to avoid these cycles in the dependency graph, and also we want to find an ordering of doing this job. Jobs, if there is no circular dependency. If there is circular dependency, then you cannot like find an ordering of, then that's like a deadlock situation. So you have, if you have something like this, you cannot perform any task, right? So that's the deadlock situation. So you don't want a deadlock situation. You want to make some progress, and when you can make some progress, when there are no circular dependencies. And so that is why you want to find an ordering now of performing the tasks. So such an ordering is called. So again, now we are going back to the graph languages, graph language. So what is the topological ordering? For a directed graph G, a topological ordering of Vg is, let's say, is an okay is an ordering, let's say v1 v2 vn, such that if vi comma vj is in the edge set, then we have, so this is a directed edge, that is vi to vj, then we have I is less than j, right? So as the last thing we had seen from Manish had said, now we are not designing the graph, we are given a graph, and now we want to find an ordering of the vertex set. So we keep the vertices in, like, so suppose these are these boxes in which we want to place the n vertices, and we want to place the vertices such that all the edges now go from this direction to this direction, right? The backward direction is not possible. Okay, such an edge should not be there. All the edges should go forward. So that is called a topological ordering. And what should be easy to see now, as I was saying earlier, that if G has a topological ordering, then G is a DAG. Okay. So let's just, like, since I didn't do the proof, like, let's just quickly look at the proof. So how will you do it? Any ideas?
So there will be no back edges. Means once we are moving forward, given a topological ordering, we cannot return to the same vertex.
Yeah, exactly. So I'll just write the exact same thing that you have said, not like, but slightly more precisely. Okay. So let the topological ordering be v1 to vn, right? And let I be the lowest index, and suppose it is not a DAG. Okay, so let's prove by contradiction. Suppose G is not a DAG, has a cycle C. So the cycle has some vertices. So let's say the lowest index is I in the cycle. So the lowest number on which any vertex of the cycle is put is I, and J is the highest. Now a cycle has path from any vertex to any other vertex, like directed path, right? That means there is a path from Vj to Vi in G. But now we have said that Vj is here, Vi is here. How can we have a path if all the edges are forward going? So you have to take a backward edge. So a backward edge. Contradiction. Contradiction to what? The definition of topological ordering. Right? Good. So this is what. So this is one direction, right? This is easy to see that if G has a topological ordering, if we can order the vertices in the graph in such a way that there is no backward edge, then of course the graph is acyclic, because to make a cycle you have to come back, right? But the good thing is that the converse is true also. That this is a characterization. That if the graph is a DAG, then you can find a topological ordering, right? So, but before we do that, let's prove a simpler lemma that will help us in proving the converse. Okay, so let's prove the lemma. In every DAG, there is a vertex with no incoming edges. And we call such a vertex a source. Okay. So how do we prove it? Ideas? So we what we are trying to show that if the graph is acyclic, if a directed graph is acyclic, then there will be a vertex which has no incoming edges. So this might not sound like very direct or very intuitive, but if you think about it for like think about it for like 10 seconds, 15 seconds, and try to think why this should be true.
We'll prove it by contradiction.
Okay, so proof by contradiction. How?
Suppose if each vertex has an out degree of at least 1, then you consider the
But
maximum.
that is not a contradiction, right? In degree, you mean?
Okay, yes, in degree.
Yes. So suppose every vertex has in degree of at least 1. Okay, that means every vertex has at least n minus of v is greater than or equal to 1 for all v. So we have started with the negation of the premise of the lemma. Okay, good.
You consider the maximal path in the graph.
Maximal path in the graph. Okay. So then, so suppose u to v is a maximal path in the graph.
Then there's an incoming edge to u, and that
Yes,
must be
that's
from
correct.
the path.
That must be from the
vertex in
path. Exactly. That must be from some vertex in the path. And then we get a cycle, right? So suppose this vertex is some w, then u to w we take from the path. So this is a maximal path. And then we have a back edge from w to u. So in total, so this is a path, and so we get a cycle, a directed cycle.
Sir, for this lemma, can't we directly use the topological ordering? Like there has to be some like for I less
We
than j.
don't know if there is a topological ordering. We have not yet shown that every DAG has a topological ordering. That's what we want to show using this lemma. Okay.
So what is the maximal path here?
Maximal path, like a path that cannot be extended without repeating any vertices.
Okay, so couldn't we just like follow one of the incoming edges from
Yeah,
arbitrary
that
node?
is also the proof. So that is the proof in the book, but since somebody suggested a different book, different proof, I just did that, and that is also fine. So what Anshuman is suggesting is that you can so suppose u is any vertex, so every vertex has an incoming edge. So this is one proof, right? Let's look at other proof. So you keep following these and you will never stop, but after n plus 1 iterations of this thing, you will hit the same, you will repeat some vertex. Because everywhere you reach, there is some incoming edge. Everywhere you reach, there is some incoming edge. So at some point, this incoming edge has to be from something that you have already seen. So then you get a cycle by following this. Sorry.
Sir, can you please explain the earlier proof that how did we get an edge between U and W?
No, so U has an incoming edge, right?
Yes,
Every
sir.
vertex has an incoming edge. Okay. If it is not from W, then you have extended the path. So your path was not maximal. If it is not from any vertex in the path, then the path is not maximal.
Sir, I did not get this. Why would the maximal path have this W which connects it back to U?
That's what I'm saying. So slowly. So let U to V be the maximal path in the graph. Okay. Be a maximal path in the graph. That means it cannot be extended to any outside vertices. Okay. There is no path which is a superset of this path, which has exactly the same edges. Okay. So that is the first assumption. Now, after that, we know that U has one incoming edge, right?
Yes, sir.
Now that incoming edge, if it is not coming from the path itself, then we get, so let's say this
we
is
extend to the
then we
left
extended
side.
the maximal path and then we get a contradiction to the maximal path itself.
Okay, sir. I think that becomes U dash.
Whatever U dash, W dash, I mean, these are just variables.
Okay, sir.
Yeah, so then we extended the path itself and then, yeah, I mean, whatever. So that means that the word has to come from the path itself and then we get the cycle. Okay, Manish?
Yes, sir.
Okay, good. So yeah, there are different proofs that we can do. So is this the proof? So Anshuman, you were suggesting this proof? The other one? That we can just follow the edges?
Yes.
This is what you were suggesting?
Yes, sir.
Okay, cool. So yeah, this is also one proof. Again, like, these things are very elementary and, very simple. So there are many ways to prove this and any of them is fine. So since this one was not in the book, I decided to go with that one which someone suggested. Like, yeah. Okay, good. So now we can show that every DAG has so the lemma that we wanted to show. Oops. Every DAG has a topological ordering. Okay, good. And what is the proof now? How can we use the earlier one to show that every DAG has a topological ordering? Any
We
ideas
start
for
with the
this?
source and remove it.
Yeah. So by induction. So base case is easy, one or two vertices by trivially you can show. Now induction step. Suppose true for n is equal to k. Want to show for n is equal to k plus 1. Now due to previous lemma, so let G be a DAG on k plus 1 vertices. Due to previous lemma, it has a source. Let's say S. So now look at G minus S. Okay. This is also a DAG on k vertices. So this has a topological ordering due to induction hypothesis. So let the topological ordering be whatever t, like, whatever v1 to vk, and then you put s in front of that. So put s before the topological ordering of g minus s, and this is a topological ordering. Why? Of g. So this is the proof. And why this is true? Why is this
Because there
s
is no
v1 to vk is Manish?
because there is no edge from G minus S to S.
Yeah, so there is no edge from G minus S to S because S does not have any incoming edges. So there are no edges which are like this, right? There are no edges like this. All the edges from S are going in this direction. And for G minus S itself, since this is a topological ordering already by induction hypothesis, all the edges are going in the forward direction anyway. Okay. So I mean, this I just said, but if you're writing the proof, you will write. You need to write this, like, couple of lines. Okay, so this means that we have gotten the topological ordering of G, which is what we wanted, since G is a DAG, and then it has a topological ordering. And yeah, so this completes the induction step, and this completes the whole proof. Good. Now suppose we want to have an algorithm also to find a topological ordering. If exists, right? So what will we do? It's a very simple recursive algorithm now, right? What do we do?
So we start with all the edge vertices within degree of 0,
Mm-hmm.
and then start a BFS or TFS, and then whatever edges are connected, whatever vertices are connected with these vertices, we'll decrease the in degree by 1, and then we'll again add all the vertices within degree of 0, and we'll keep repeating until there is nothing left.
Yep. That's correct. So let's build towards that in like slightly gradual way. So that's very nice, but might sound a bit complicated to somebody. So let's just like find a source V. Okay, make it the first node, and if you cannot find, then just say that. Then say no. Okay? So if it exists, so find a source V, make it the first node in topological ordering. Second, delete V. And third is find topological ordering of G minus V recursively and place it after V. Right? So this is just what we had done earlier. We have just written it in an algorithmic form, but we'll see how to do this. And the correctness is now follows from the lemmas. That we know from first lemma, if G is DAG, or second lemma, I don't know, DAG, then it has a source, and follow the proof of the last lemma to see that it actually produces a topological ordering. Again, like, you can do by induction by the number of vertices in that. Suppose the algorithm produces the correct topological ordering for k number of a graph on k vertices, then assuming that you so as you will do always with recursive algorithms, you do it by induction, the correctness proofs. Okay. So similarly, you follow the previous proof, you get the correctness of the algorithm. But let's do some running time analysis, right? So in each iteration, finding a source V and deleting it from G, how much time that can take? Order n time in worst case. And then since there are n vertices, n iterations of the algorithm, so total time order n square, right? But now we want to be a bit clever and do this in order m plus n. Okay, so now we'll try to do what Mani was saying. Okay, so we'll maintain two things. So better algo. What do we maintain? So first, like let's call a vertex active. If it has not been deleted. So in every stage, the algorithm deletes one edge, one vertex, right? So a vertex is active; it has not been yet been deleted. So we maintain two things. First, for each vertex, number of active vertices that have an edge. So each vertex V, number of active vertices that have an edge to V. Okay. So you have V, and then there are some vertices which have not been deleted. So there are some which deleted. So this will not count. So suppose this number is going to be 3 here for V. Okay. So call this A of V for now. Okay. And the second is a set S of active vertices which do not have incoming edges from other active vertices. So in the graph that we have currently, these are the sources that we have. So there is this vertex, it has some, okay, no incoming edges, right? Sorry. So it has some outgoing edges to other vertices which are blue. So let's say blue is the active ones. And then it might have some incoming edges from red, but that we don't count. So this still belongs to S. Okay, at that stage. Sorry. Good. So now initially everything is active. Okay, so initialize A, V, and S in order and time. So AV you just go through, sorry, AV in order M time maybe, because you have to go through all the edges to see that how many incoming edges a vertex has. Okay, so you just initialize this, and initially the set S you go through. If a vertex does not have any incoming edges, initially everything is active. So if a vertex does not have any incoming edges, then it goes to S, right? Okay, now in each iteration, pick a vertex from current S. Okay, so you pick the vertex V, let's say, from current S. Look at its outgoing neighbors. Look at, so pick a vertex V, let's say. Look at V plus, sorry, N plus of V. So look at all the vertices which, okay, and decrease their count, their A count. So look at V W in n plus V and decrease AW by 1. Why? Because you are going to delete V now from the graph. It is not going to remain active. So one edge will decrease from all these vertices. So they will have one less active vertex from which they have an edge. So this was W. So W used to have many active edges from active vertices, but now it will have one less because we are going to delete V. Now also if AW becomes 1, becomes 0 in this process, then put W in S. Okay, so now this will now give us the new sources that, okay, we started with some source and then we looked at its outgoing neighbors. So new source can only come from either it was already a source or it became a source after deleting these vertices. So new sources can only come from deleting these vertices and hence these edges. So that's what can make these guys in degree 0. So then we add them to S. So either there are already some sources or we get new sources by deleting the current sources, right? So this is the algorithm that we keep doing this and finally we keep picking things from S, right? So what is for each, what is the running time now? For each edge now, we are doing order 1 work, some constant time work. What? For each edge when we traverse. So initially we did this order M work. So we have now set up after the initial setup, let's say. Even in initial setup, we are doing order 1 work for each edge. But let's say we have initially set up the things and that is order M. We have already done. We have set up the set S and we have set up the list A, this list. Now, after that, we go to a vertex in S and we traverse one edge. What do we do for this one edge? For this one edge, we decrease its A count for this W. And then if AW is equal to 0, then we put S is equal to S union W, something like this, right? So this is all we do for one edge. Then we traverse another edge, then we traverse another edge, then we delete V from the graph, right? And then again, we repeat this process. So we take order 1 time for every edge. So this is order M plus N time again. So in order M plus N time, you can actually find whether a graph is DAG or not, and you can actually generate its topological ordering. Okay, and the correctness we have already argued. We are doing exactly the same thing as we were doing in this simpler algorithm. Where is the simpler algorithm? This simpler algorithm, we are just doing it more like, we are maintaining some other information so that we can do it fast. So the correctness remains exactly the same. Any questions about this?
Sir, could you please explain the running time once more, that how it's order M plus N?
It's order M, that you agree?
Yes, sir, first that.
Okay, so it's order M. Now you also have you have to go through all the vertices to check whether which ones don't have any incoming edges. So that will give you order N. So you need to make the set S, right?
Yes, sir.
What is the set S? Set S is the set of all vertices which don't have any incoming edge, right?
Yes, sir.
So for that, you have to go to at least all the vertices, even if they don't have any edges.
Sir, but every time we are iterating from any vertex, we are looking at the edges. Means the edges which are means which are
No, we are
connected.
not. No, we are not. We are just picking a vertex from S. So maybe the graph does not have any edges. Maybe the graph is empty. Still, the topology will be all the vertices,
Okay.
right? And then you will just vertex from S, another vertex from S, as so on. Still, the algorithm will order n time. For an empty graph, let's say. So whenever you thinking about this order n, why is it coming or what? So these becomes important only if n is more than m. Case with suppose, so whenever you have to think about it, an empty graph disconnected, what the or has very few edges, then what the algorithm will have to do, and maybe then you will get. Rishabh, do you get it that for empty graph the graph will take the algorithm will take order n time?
Yes, sir.
Okay. So yeah, so if you're thinking about order n, then think of an empty graph generally. That makes things easier to understand. So yeah, maybe I should have said initially for setup, maybe I should have said order m plus n time, not order n time. Good. Any other question?
So can't we just use the DFS algorithm to find topological sort?
How?
First, we maintain the visited list, and we iterate through all the element vertices. And if any vertex is not visited, then we start the DFS. And
No,
after the
no. So,
DFS,
but it is not visited, right? So, how do you guarantee that you're getting a topological sort? Because there should be no backward edges. DFS has many backward edges, if you remember.
yes, okay, yeah. I'm just saying, assume that the graph is directed acyclic. It's DAG. Assuming that it is DAG, then there will be
Yeah.
no
So
backing.
even though it is DAG, I'm not sure why it will give you. So suppose this is a DAG. Oh, so assuming that the graph is a DAG, okay,
Yes,
but then you
and
need to find out because
and also you can just do like this. When the DFS starts, you make the visited true, and inside and at the end of the DFS call, you make the visited false. And if the and if you're visiting the any other vertex from this adjacency list, then if that vertex is already visited, that means that it is a back edge, and that you can say it's directed. It's not directed, it's not acyclic, so therefore there is no topo sort. So now
yeah,
and
yeah,
we
yeah.
make
I think
and we
what
make
you're saying can be implemented as an algorithm, and there might be some way, but there is a caveat that you need to know that this. Okay, no. So you are saying that this can even be found out
yeah.
to. But how do you know? You need to find a source, right? Because even the first
Yeah, no,
vertex that you start.
exactly. Exactly. So what happens is you take the source and suppose you maintain the topological sort
But
list
here
and
also you're doing the same, right? So the whole complexity here also is for the source only. That if you can find a source and then for doing things again. So we are running out of time. I don't want to take too much time for this. If yeah, if you have a proper if you can write it down slightly well so that I can also understand it better, and then you can ask in Piazza or in the group. That will be I think a more conducive way to understand it and explain it also. Ayush?
sure, sure.
Yeah. Sorry for not being able to take it, but we are very much out of time. Okay. And I'm not doubting that it cannot be done. It's just that I'm finding it slightly hard to understand exactly how it will work. So if you can write it down as an algorithm, it will be easier for me to understand also.
Okay,
Okay.
I'll do it on Piazza. Okay.
Okay. Okay. So thank you everyone. So and see you on Tuesday. Okay. Thank you. For those who are till now, you can ask if you don't have a class, and if it is a short question or something. Okay. Thank you.